So now understand that is a UTM is first universal testing machine, and we are studying it because it is in your syllabus. So now I hope you remember the cross section, how the cross section of the specimen is. This is the cross section of the specimen. There is no need to worry about the dimensions because dimensions is not coming. I'm just talking about the concept. So this is the place where the grips are present. So this is the grip, you can see this is the grip and this is the grip where you can hold the, and it is either hydraulic operated or manually operated. And when you apply the load and you pull it from here, then this is the length where the deformation is there. So suppose this is L0, and then the deformation, and you gradually applying load. So uh, let me do something like this. So now suppose this is your now what I'm trying to say is how we get it. Now you apply force, and this is the deformation or exact length, you whatever you want to say. You apply force, this will go on increasing, and then for mild steel, especially I'm saying for mild steel, this is go on increasing, and then there is coming a sudden drop, and then again it will increase and go on. So let me point out, this is point A, this is point B, this is point C, this is point D, this is point E, this is point F. Now point A, it is called proportional limit. I hope you remember the few minutes ago I talked about that thing. Point B, elastic limit. So what is the difference between proportional limit and elastic limit? Any idea? Any guesses? I'm waiting for single. If you go and message me just something, what is the difference between these both? Just you can unmute and say anything. Uh, no one is saying anything.
Sir, in elastic limit, the body returns to its retains its shape after removal of the force, and in the proportional limit, the it follows the Hooke's law.
Okay. So yeah, he is right. So means elastic limit, the body will recover its shape to the original. Means that there will be no deformation. But the Hooke's law is applied to proportional limit. It will not applied here because there is slightly bend, and it is not a line. For the Hooke's law can be applied to a line. So he is right. Why I want to say this, because in PSUs, I know if you know every PSUs are giving their own exam. You want to go in PSUs, you want to write every exam, and their question is not from coming from gate directly. They ask these simple questions. Whose law is valid up to proportional limit, elastic limit. Now you got confused. Where what should I pick? I hope you are getting it. For PSU, there is not a gate exam like gate. I hope you remember just recently HPCA give the exam. In that you have in 2 hours, means 2.5 hours, 150 minutes. In 150 minutes, you have to attend 170 questions. So you know that if it is gate, you cannot do that. In gate, you have one question, 3 minutes. But in HPCA, so the question is directly. Now it is a just 10-second question. If you know the answer, you just click it. Which is the what is the answer? But if you don't know the answer, how you get it? So that's why you will also remember the concept, because every PSU is giving their own exam. Now what is C? C is the upper yield point. D is lower yield point. And if you perform the experiment, I hope you all get it for mild steel. This graph, everyone gets it in their experiment. E is called ultimate because it has a peak, means this is the peak value. This is ultimate. And F is fracture strength, fracture stress also, fracture stress. So I hope elastic proportional limit, Hooke's law is valid. Elastic limit, we know that up to the body retain its soul shape. Yield point, after that plastic deformation takes place, means the body is not coming its back to original position. If we just release it here, it will come like this. It will not come back to its original position. It will come like this. And this is the permanent deformation. So I hope if you got recently, a question came in GATE this 2021, I think, given that this point and ask us to find the permanent deformation. So I will get to that in just after a few minutes. So this is the upper yield point. T is a lower yield point. Someone just unmuted it. Uh, who is unmuted? I think someone is just unmuted. Okay. Now E is the ultimate stress. F is the fracture stress. So everything ultimate stress means up to which after this you can say the necking starts means after this necking means the body will shape like suppose this is your body and the cross section will gradually decreasing. This is called necking. It is formed like a neck, and after that it will break. Now a question also come cup and cone failure. Which material performs cup and cone failure? So every ductile material performs cup and cone failure. So now you got it. I think so. Cup and cone failure will be like this. Suppose this is a cup, and suppose this is like failure. And brittle material. I think I should move to the next place. In brittle material, suppose brittle material. If you plot the graph will be like this. There is no any yielding point, there is no any that point, it will simply go like this. So okay, now that's you can show or you can see that that's why brittle material are unpredictable to failure. Why? Because there is no yielding point. In the mild steel you can easily see that there is a yielding point, there's a plastic deformation zone. Means suppose you, if you apply a force, you are using a body and you apply force, you can see that oh the yielding is started, now I have to reduce the weight so that my body will be safe. Now in brittle material there's a sudden failure, means there is no yielding, you gradually go on increasing and suddenly the point the body breaks. So that is a disadvantage. That is why mild steel is usually used so much, because it shows the characteristic of entering from elastic to plastic region. But in these brittle materials, we don't know where to stop. It will not show any permanent deformation, much deformation, and then suddenly it breaks. And you need to know whether you are exceeding the limit of stress or load or not. So brittle material, they just simply this simply break like this. So so you need to know that cup and cone failure occurs in the brittle ductile material. So anyone wants to write it anything or just I'm giving 1 minute and I'm going to.
Sir, excuse me, sir. Sir,
Yes, yes, tell me.
Sir, can you explain one more why the curve decreases from point C to D, sir? I didn't get it quite well, sir.
That curve D, actually, in that thing, the you can say there's a permanent. We can say this is a reason where material settles itself. Means, suppose you applied the load from point B to C. Now the load is exceeding the limit, and the material is settling itself to the new configuration. So there is a increase in deformation, but the load, you are not increasing the load, but there is continuous deformation is there. And after that, when it settles to the new place, means the crystal orientation changes. And when the crystal orientation changes, then it will again behaves like a new material. So that is the only advantage of steel, using mild steel, is it shows these points. And I hope you are going to have manufacturing classes. You asked the question about quartal atmosphere. What is quartal atmosphere? Because it is a manufacturing science subject, I don't know much about that in depth. So I hope ask them about the quartal atmosphere. They will make you understand why this is coming. In crystal structures, why this is coming. You can ask that question. Why quartal atmosphere important? I hope you get it.
Yes, sir.
Okay, so ask that question because this is an important significance because of this atmosphere present in the crystal structure. This is coming, and this is only coming for mild steel. Suppose uh, you have aluminum. Okay, just write it. Then I will coming. Hello. Okay, I'm going. Suppose you have a material because everything is not mild steel. Now, suppose if a material is there that is not showing, suppose a material other than mild steel, and it is ductile. So let me take some, and you just apply the load, and it is showing behavior like this. Now, this is generally for aluminum. This is coming from for aluminum. Now, what is the yield point? Anyone is getting? There is no yield point is coming in this picture. Now, I hope you are getting it. What I try to say. Other than mild steel, okay, other material, mild steel, no. There is no yield point is coming. So how you get to know about the yield point of this material? You know the ultimate strength, you know the fracture strength, but there is no yield point. Okay, you can get the elastic limit when it is falling because after that the slope is changing, so you can get elastic limit. But in this reason, you are not getting anything about the yield point. So what you should do is follow the take the deformation of 0.2% here, and just plot a line equal to this slope, and where it cuts this line, this is called the yield point. Now, I hope you get it. So take 0.2% or 0.002, that is epsilon value. Take this value, plot it like this, parallel to this line. It should be parallel, means the slope should be equal to elastic modulus. Okay, and where it cuts this line, this is called the yield strength or yield stress. Okay, so this is for aluminum particularly. So this year in HPCL, they asked this question: for aluminum, what is the percentage for which you can consider the yield strength? And it is the value is 0.2%. Okay, so in HPCL, this question is asked. So that's what I'm saying, and I'm looking for it in the paper. You cannot obtain the yield stress in this condition, so you need to go through this. I hope you understand this thing. Okay, now where we started, UTM. So in UTM, the elastic limit, these the elastic modulus. So when you know, when you protect the graph below proportional limit, just go it like this way: E is equal to sigma proportional minus 0 upon epsilon proportional minus 0, and you obtain the modulus of elasticity. Okay, because it is tensile stress. So this value you get in that thing. So this from these equations you can derive, from UTM testing you derive the material property, that is modulus of elasticity. Okay, now same thing you can, it is in for tensile. You can do the same thing for compressive also. Just apply the load in the opposite direction and check how much it load can it sustain. And then for compressive stress, you can get compressive compressive force. You can get that modulus of elasticity. That's why the UTM is used. UTM is used now. UTM is used to obtain the first of all stress strain curve. First, we obtained force deflection, then we change the dimension. We divide the deflection by del L, and we change the force by divided by area. So it changed to stress strain. So we obtained stress strain diagram. We obtained proportional limit. These are the findings of UTM testing. We obtained the elastic limit. We obtained yield point, ultimate strength, and fracture strength. So these are the findings of UTM. So I hope you got clear in UTM. So now elastic constants and relations. So you know there are three types of elastic constants. Elastic, that is Young's modulus. Let it denote by E. We have bulk modulus, that is denoted by B, and we have shear modulus, that is denoted by C. So I'm going with direct expression because we don't have time to prove it, or just exam there is a direct expression you need to know. Is equal to 3b 1 minus 2 mu is equal to 2c 1 plus mu. Now what is mu? Mu is equal to minus lateral strain upon longitudinal strain. Now what is the meaning of mu? And it is called Poisson's ratio. Poisson's, I think the spelling is Poisson's, whatever it is. Poisson's ratio. So what is the meaning of this? Suppose you take a rod, you apply a load P. So that volume is held constant and the dimension will change. Suppose this is the dimension. Now from L0, it changes to L1. And from uh, D0, it changes to D1. Now the diameter is reduced, but the length is increased. Hence, volume is held constant. So you can say area A0 L0 is equal to A1 L1. Now the lateral strain will be uh, its change in diameter d0 minus di upon d0, and longitudinal strain will be, longitudinal means in the direction of force, lateral means perpendicular to direction of force. It is L1 minus L0. So we can write it delta d by d0, and we can write it as delta L by L0. So now mu will be minus delta d by d0 upon delta L by L0. Now why minus is coming here? So if you look at it, I think I should do it in like this way, d0 minus d. Now why minus is coming here? Because lateral strain is in negative direction, negative value. It has a negative value. Now in order to make the Poisson's ratio positive, it is multiplied with negative, because delta L by L0 is a positive value. Okay. And you need to know the these relations need to be memorized, because suppose you have given elastic modulus and you are going to ask in question in bulk modulus. You need to know the mu value. It is given in the paper, so you can convert from bulk elastic modulus to bulk modulus, and you can obtain the change in volume. And if you are giving Young's modulus and you need to obtain the shear modulus, one last question, this question can be asked. Okay, so remember this formula. I always say this is a very important formula because it is very confusing. You can see it, how you can remember it. So you need to know this. So just write it. Now I am going to with a trick how to remember it. Okay, so listen properly. Hello, I'm audible.
Yes, sir.
Okay, so I am going with a trick. Ignore minus sign. What is 2 plus 1? That is 3. And what is, suppose what is in front? 1 na? What is 1 plus 1? 2. Now go with it. Remember this thing, 1 plus 2, 3. Put it here. And now it should be 3 na? So 1 minus 2. And what is 1 plus 1? It is 2. So remember the coefficient. I hope you got the trick. So I usually learn it in this way. So it is 1, 2 plus 1, 3, and t is coming, 3 is coming here, and it is 1 plus 1, 2, 2 is coming here. Ignore the minus sign and then adjust the inner thing in that way. You always gonna remember this. Now, if I talked about Poisson's ratio here, so let me go with Poisson's ratio. What is Poisson's ratio? So mu is called Poisson's ratio. Spelling is P-I-S-S-O-N. Poisson's. It is minus del d by d0 upon del L by L0. So its value is typically from minus 1 to 0.5 for all materials. All materials. And for especially for metals and everything, it is from 0 to 0.5. Now, for metals, and it should not be greater than 0.5, and 0.5 for the perfectly plastic body. perfectly plastic body. Okay, for metals and all. Now, I think everyone knows the cork. Cork, you know. So cork is a material that is used to that is put inside a bottle that is pressurized. I think in wine bottles and everything, it is stored by a cork. So I why why don't they use any other thing to stop it? Why cork is used? Any guesses? Why it is used to stop press means make it the bottle as a stopper? So let me tell you, because it has a Poisson's ratio 0. Now, what is the meaning of this? Let me explain. Suppose you have a bottle and it is pressurized. Means pressurized means this contains some gases to make it up in a pressurized way. Hello. Okay. So now they put cork. Now suppose if they put any other material, suppose other than cork, that it would make contradiction. Then there is a pressure force that is compressive in nature. Okay. Uh, are you getting it? So suppose this is a cork or metal, any material, and you apply compressive force, and because it is fixed from here, so it will just a reaction force is coming backward, F. Now what it will trying to increase the cross section. Why? Because it is compressing the length, and when the length is compressed, because the volume is constant, diameter will increase. Okay, then this diameter, because the force is compressive, let me write it, otherwise you all gonna mash. It will reduce the length. Now, because volume is constant, reduction in length will make increase in diameter because of the Poisson's ratio. Remember Poisson's ratio, uh, del D by D upon del L by L. So if that is gonna decrease, then their increase in diameter because of the volume constant. Now, increase in diameter will lead to the, if we just increase the diameter, then it will also creates a problem in means the material will change its diameter and fit it like in this way that it can also rupture the neck. Means it go on increasing and it can rupture the neck, or it will like in this way that it will not come outside. Now that is the importance of cork. It it has a mu value of 0, means there is no any lateral strain. Means if you go with this and you have change in length, then the increase in dia is not possible in cork. Now that will, because the diameter is not increasing, the cork can be easily pulled outside. So I hope you got it. Just say yes, I am audible, everything is clear, so I can move ahead. Any message? I'm waiting. And I will move ahead.
Clear, sir.
Okay, then the use of cork is clear. Okay, now the testing of impact, that is also in your syllabus. The testing of impact, that is ISOT test and Charpy test. ISOT, it is ISOT and it is Charpy. Now I am just giving you the differences and how you will measure it. You know that this is like simply supported, and this is like a cantilever. I hope you are getting the concept. Means it is hinged from one side and the impact load here. So the differences between Charpy and ISO. First of all, their dimensions are different. So here it has 55 cross 10 cross 10. it is around 75 cross 10 cross 10 mm dimensions of the specimen. Here, the impact load is from behind and at center. Here, it is at top and from the front. From the front. It is a Sharpie V notch test. Sometimes it also uses VU and V, but here it only uses V notch test. Okay. Now, the hammer is different. It is also, but that is not for importance. So, okay. Now, this is I hope you remember this machine. This is used to measure the toughness. So basically, in impact loading, we measure the toughness. Toughness is, I will go with definitions that toughness is the area under stress strain curve. Area under stress strain curve. Now, what is the meaning of this? As you know, stress strain curve, let me write this. Stress strain curve is plotted up to rupture point or fracture point. So if someone is taking the area, then it is taking area up to fracture point. That means toughness is toughness is energy required to break the specimen. Energy required to fracture the specimen. Fracture the specimen. That means the whole area under the stress strain curve, it gives the value of toughness. Now area under stress strain curve is plotted up to fracture. That means toughness is the energy that is required to fracture the specimen. So in this, what you load, you just simply load the hammer up to certain height, pin it here, place the specimen, and just say drop it here, and it will swing like this. So initially it has a height, so it has a potential energy of mgh, and after that when it reaches to this height, it has a potential energy of mgh small h. Now the difference in energy delta E, that is equal to mgh minus mg small h. This is the energy that is absorbed. Absorbed where? Absorbed in the material to break the specimen. Now I hope you everyone get it. So in UTM, what we obtained the points, and in ISOT Charpy test, we obtained the toughness of the material with different notch. It is like a cantilever, it is like a ISOT test. Sorry, it is like a cantilever, it is like a simply supported beam. So anything these are simple things just need to remember, because it can ask in PSUs that where are the impact loads. So remember the concept, don't go because, and what we obtained in impact testing, we obtained the toughness, because toughness is the energy required to break the material. How tough you are, there's different thing, strength and toughness. uh, how much, what is your strength, how much you can deal it, but means normally your power. Suppose someone asks what is your strength, normally your power. Now you, how much you are tough. Tough means you are given certain work that is against your limit, and you are using that limit to do the work, that is called tough. So strength means the normal power or normal work or normal strength. Toughness means how much you can take the load before breaking. So if you resemble it from your way, then it will more easy. Now testing of hardness. So basically there are three types of test. I am again going in theoretical because these are three things that are coming in the exam and you need to know this. Now Brinell hardness take, Vickers hardness and Brockwell hardness. So first, this is a theory, you can write it simultaneously with me if you want or take a screenshot. Brinell hardness test. First of all, what is the material? So the material is hardened steel. Hardened steel. I am suggesting please write with me because it is all theoretical. Shape is spherical ball. And which type of material it can apply? For apply material applications, any soft material, any soft material. Soft doesn't mean rubber. Soft means mild steel, aluminium, low carbon steel, and copper. Now, the its principle is it is applied on the principle that area of indentation, how much indent it will go. So the number of Brinell hardness number is equal to P upon pi by 2 uh, d minus under root d square minus d square. So what is the meaning of this? Suppose this is a ball that is spherical ball that is applied and put on the material. Okay, you apply force P. The diameter is capital D, and this has a diameter of small d. Now the brittle hardness number is P, that is load, that is in kg, and these diameters are in mm. So please write this with me because otherwise you will search in Google. So this is the brittle hardness number. A spherical ball is placed. It will you punch the ball with a load in the specimen. Then you take out the ball. You measure the diameter, and then the brittle hardness number is calculated. So this is the brittle hardness test that is performed. That is for the soft material, that is mild steel, aluminum, low carbon steel, copper. Now the second is Vickers hardness test. In Vickers hardness test, the material that we use is diamond. The material that we use is diamond. Its shape is pyramid with square base. Square base. It is applicable to hard materials. The application is hard materials. That is high carbon steel, silicon carbide, and tungsten carbide. And in this, the diamond is not penetrating. Diamond is just scratching the surface. Is just scratching the surface. Scratching the surface. And the Vickers hardness number is 1.854 P upon D square. And here that D is D1 plus D2 by 2. Now what is D1 and D2? D1 and D2 is, suppose this is your tool. So let me go with this. This is your tool, and this is 136 degree, which is pyramid shape. And if you look at from the bottom, then it's shaped like this. It has a square shape that is pointed downward, and these are the two diagonals. So this is D1 and the second diagonal is D2. So this is the value. Okay. So that is on the surface. The puncture is we obtain the D1 and D2. So this is just theory. Just write it. I can't do much in that because, but you need to know everything.
So can you explain D1 and D2 once again, sir?
So actually, if you just I should take either I should take a Google photo. Okay, let me think. So this is the material. Diamond is a pyramid shape with a square base. That is written square base. So the base of this pyramid is square like shape, means it is cut like in this way. Okay, means the base is square and it is cut like this way, and when it is penetrated on the body, then it will leave an impression like this. So you measure this D1 and D2 by my microscope. There you, I hope you see the low precision microscope they mount on that, and you measure D1 and D2, and then that D1 and D2 by 2, that is the mean of their diagonals. This is the length of diagonals. So they take the length and mean that, and then the Wicker hardness number is calculated. I hope now it is clear. Otherwise, I should take a photo from Google explain, because 3D I cannot draw.
Clear, sir.
Okay, 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 okay. Now the third is just theory. I can't do much there. You have to write now, and it will ask an exam materials or anything in any PSUs in any paper. These things are common, and you need to know that. The same thing, the material is diamond, but this time the shape is conical shape with 120-degree angle, and this is for every hard material. This is for every hard material, and here uh, is direct formula. This is not given. It is direct inversely proportional to depth of penetration. So I talked about the three major tests that is performed for hardness. Now, someone asked me, or you are going an interview, and someone can ask, "What is hardness?" So, what you say? If you go in IITs for interview for MTech, they gonna ask the basic definition. Don't expect they are going to ask what is means how you produce the impression of this. They will never ask like, they will ask direct to, means I'm in ISC. I have faced almost all top IITs interview to and now I'm getting a PhD here. So I know they will never ask you anything very hard and fast. They will ask only these basic. What is hardness? So what is hardness? Can anyone say? Because I hope you are in third year and final. You just in first year everyone knows these things in mechanics. Any message? Anything?
Ability of a material to resist indentations or scratch.
Yeah. So that what I this is the definition, and you need to know that the difference is that hardness is ability to resist scratches. Means suppose you know the diamond, just scratch it, it will not gonna scratch you. But if you take a rubber, you scratch it, easy, you can do it. But in material, the same thing happen. For soft materials, it is easy to scratch that material, but for hard metals, so this thing basically you remember this, when carbon content increases, carbon content increases, material becoming hard. Okay, so low carbon steel, mild carbon steel, mild steel, that is called mild steel, and high carbon steel, high carbon steel. So as we go downwards, the hardness increases. Hardness increases, ductility decreases. So remember this thing. Whenever carbon content increase, the ductility will increase. The carbon content increases, hardness will increase, and ductility will decrease. So that's why soft materials is mild steel, low carbon steel, and we all know aluminum also. Just like aluminum foil, aluminum is easy to scratch, and that's why it also has a low melting point. And weaker hardness test, high carbon steel, silicon carbide, any carbide, silicon carbide, or tungsten carbide are very hard. Then these are the three things for hardness. So let me get a quick response. Three testing are clear to you. Hard UTM, impact, and hardness. These are theory portions. That's why I completed in first lecture. So are you got clear the basic principles? Just type yes or no. That's then I will move ahead. Okay, okay. Now, simple stress strain problem. So, now this is a basic problem. I hope everyone knows this, but I need to go because suppose this is a body that is applied load P. This is the area of cross section is A and the length is L. The elastic modulus is E. So, you need to obtain the strain. First of all, what is the stress? Stress is equal to P by A, the first equation. And from Hooke's law, we know that stress is equal to Young's modulus into strain. And strain is delta L by L. So we don't know this, we know this. If we put that together, it is like P by A is equal to E delta L by L, or delta L is equal to E L upon A. So it's a simple stress, and for every question that I'm going to discuss after this, delta L, that is the elongation in length, is PL upon A. P means applied load, that should be in Newton. It and this should be, it is given in paper, it is gigapascal, but you need to convert multiplied it to 10 to the power 9 to convert it Newton meter square or Pascal. Now area of cross section, it should be in meter square and length should be in meter. So this is the basic formula, and believe me, this is the only formula that is applied everywhere in zone, and up to three chapters, I think. PL upon A. If you applied load, and you know we can reduce easily. So where I should leave? Give me a question. Suppose you have a body. Hmm, it's not very properly. Let me take. Suppose it is a combination of three bodies. Okay. So a sec. You can see this is here. This is portion A. This is portion B. This is portion C. This is portion D. This is portion E. Now you applied 10 kilonewton here. You applied 80 kilonewton here. You applied uh, 50 kilonewton here, and you applied 30 kilonewton here. And everything is 100, 100, 100, 100. Everything is mm. So and the area of cross section is 500 mm square. area cross section is 500 mm square, and given E is equal to 80 GPa. Now you have to obtain the total elongation of the bar. So uh, I'm let's just think. I'm giving you 1 minute. Think about it. Then we are going to come in this point. How we do? Okay. So this is the first. What you need to do is that means there is no need to use this thing. So first body. This is your first body. Yes. Suppose this is your first body. This is your second body. Uh, this is your third body, and this is the fourth body. So first check the force is balancing or not. It is coming. This is forces. Okay. So here 13, 40, and 48. So if you take 10 Newton here, so and here is 80 Newton. So what is the force in this direction? No, suppose this is your 10 Newton. Okay. This should be 100 Newton. Now it's balanced. Okay. Suppose this is 100 Newton because it is given. Now here it should be also 100 Newton because it is in equilibrium. Now here it is given 80 Newton. So what you need to do is put 20 Newton opposite direction. Then the net resultant will be what will be? It is 80 Newton in this direction. Now since this body has 20 Newton in this direction, put this 20 Newton here also. And there is no any constraint. So let's leave it here. And after that, no, there is no any force. That means zero force. Zero force. So 20 Newton here, put opposite 20 Newton. And here you will get 20 Newton because the body is in equilibrium. And since it has 50 Newton, so and you have 20 Newton, so you need 30 Newton here and 30 Newton here. Let me explain it again. Suppose these are the forces. Okay, so this is a 100 Newton force applying on the 100 kilonewton. Okay, so put that force here. Okay, now as the body, every body is in equilibrium. Suppose whole body is in equilibrium. Whole body is in equilibrium. So every body also in equilibrium. This is the basic principle. So 100 Newton is pulling this object here. So it should be 100 Newton here also. But as you know, there is 80 Newton force, 80 kilonewton force. So apply 20 Newton in opposite direction so that the sum is what? 80 Newton. And here we have zero force. So the net should be zero. Then if because you have 20 Newton this place, so that same force will come here. And it has zero force, that 20 Newton in opposite direction. Then here again sigma is zero. Here you have 50 Newton in this direction. You have 20 Newton just because you just put it 20 Newton here. It should be equal to 20 Newton. And it should be 50 Newton. So the net force will be 15. And just because you have 30 Newton and equilibrium, you have 30 Newton here. So any problem in this question? in up to this part.
Once again.
It's let me proceed further. So A, B, B, C, C, D, E, E. Now the concept, the total elongation will be, of the bar will be total elongation will be elongation of AB plus elongation of BC plus elongation of CD plus elongation of DE. So what is the elongation of AB? PL upon AE of AB plus PL upon AE of BC plus PL upon AE of CD plus PL upon AE of DE. Okay. Now, if we up as we know every individual force. So for this you have 100 kilonewton force. So multiplied with 10 to the power 3. That is every dimension is 100 mm multiplied with 100. And why I am putting 100 mm, I will explain it here. Now here the area is 500 mm square. Let's put it 500. And your 80 gigapascal, you convert it to megapascal and write it as 80 into 10 to the power 3. And for same every other cases, this also, this also, this also. So just do it. I am giving you 2 minutes. Okay.
Sir, it's PL by AE only, no, sir.
Wait a sec. Just do it. I will compare it. Hello. Yeah. Any question from I just hello.
No, sir, clear, sir.
You have any question?
No, sir, no, sir.
Yeah.
Yes.
That elongation, that part you are coming considering now, that is compression. So take it negative now. It as per the sign. Okay. Don't worry about it.
Okay, sir.
The load as per the load, take it negative. So means elongation is if it is extending, you have to take it plus. If it is reducing, you have to take it negative. So I will leave it too because I don't have enough time for so. Uh, they give me 25 hours to complete so, and in every other coaching, they're about mm, around 1.5 months. They teach continuously. If you go in any coaching, so I have to constant go with it because I'm trying to explain the principle of superposition. So principle of superposition. So now you understand the elongation will be their individual sum. Okay. Now I'm giving you a question. Solve it as your assignment, and I will tell the answer straight. So it has three parts. Three. You have loads like 40 kilonewton. You have 30 kilonewton. You have 20 kilonewton, and you have 20 kilonewton. So first check the sum. It is in equilibrium or not. Because other it is not in equilibrium, then your body will not be in equilibrium. So what will the sum? 20 plus 30, 50 plus 40, 90, and here also 90. So body equilibrium. Don't worry about it. Now the length is 750 mm, 1000 mm, and 750 mm. Their respective dimension. If this is 50, don't confuse. 750 mm. So let's make this more clear. Okay. Now given E is equal to 200 GPa, area of cross section is given 600 mm square. Then find the total elongation. Total elongation. Okay. The answer is 1.4 mm. Okay. Take the screenshot, solve it by your own, then you understand the concept of superposition.
Sir, for the last term, what are the lengths, sir? For the last term.
Last term, length is given 750 mm.
For last term, sir. Last term. Before, sir.
This,
Everything 100, sir.
yeah, have everything is 100.
Okay, sir. Okay. Thank you.
Okay. So write this question, the answer is 1.4 mm. Okay. Now let me go with this combination of stresses. So you can just the things. Now we go with combination of stresses. Just I talked a few minutes earlier. Um, you can just like normal stress. Normal stress. So normal stress is either tensile or compressive. So tensile is positive, compressive it is negative. Compressive it is negative. Shear stress, it also has positive and negative, and I will tell when. When I will tell in next next page. So suppose this is one kind of stress, this is one kind of stress. You can perform binary operation in between these two, but you cannot perform binary operation in these two. Okay, let me give you an example. Suppose you have a stress like P, or sorry, sigma, and you have again a compressive stress like sigma C. Then you can directly perform sigma minus sigma C. Okay, but if you have a stress like sigma and tau, so how will you perform the stress? Because these are two different kinds of stresses. So they are not like they are not like. So you cannot perform direct binary operation. Combination of stresses cannot be performed. Cannot be. So that's why you need some solution. Now again, one thing more. Let me clear. Okay. Suppose you have a body and you apply stress sigma 1 here and sigma 2 here. Now again you cannot perform binary operation here. Why? Because they are on different planes. You cannot perform it. What is the stress in the body? Suppose you take a plane arbitrary at an angle theta and you want to know what is the stress in this plane. So you might think that okay, that forces are tensile, the stresses are tensile. So the stress on this plane is tensile, but no, they don't have tensile forces. They have tensile as well as shear forces. So how they are coming? So these type of problems you need to know how to solve, and these are the basics. And these I just they are starting point of some. Means I just introduced you the basic concept, but these are the starting point. How to deal with different kinds of stresses and how to deal with on different surfaces. So that's why we need a Mohr circle. Okay. So this is why you need a Mohr circle. I hope everyone read it, but let me clear. Suppose you have a body and you apply force sigma 1 here. Okay, and here no force, 0. Sigma is equal to 0. And no tensile force. So plot sigma 1, it is has an axis of sigma and tau, means axis of normal and shear stress. And you just plot, this is a 0 0. So first of all, sigma 0 lies on this point. So this is sigma 0 is equal to 0. And sigma 1 lies here. Sigma 1 lies here. Because it is tensile, so it is lying positive axis. If it is compressive, it will lie in negative axis. Okay. Now you draw a circle in between. You draw a circle in between. Okay, like this. And now these are the uh, these this is a end point and this is the end point. So the center of the circle must be sigma 1 by 2 comma 0. Now okay, now suppose you need to find stress at any section theta. Okay, now this theta, or you can say this theta. So it is from this plane, it is at angle theta in this direction. You can see anti-clockwise direction. So take this line as this plane, and in anti-clockwise direction, where is anti-clockwise direction? This direction. Mount is like 2 theta. Take angle 2 theta and draw a line and let it intersect somewhere here. So this is the value of shear stress. Okay, let me do it with different pen. So this is the value of shear stress, and this is the value of normal stress. Okay. Now suppose in this plane. Now if you change the plane, you change the plane to like this. Suppose you take theta is equal to 90 degree. Theta is equal to 90 degree. Now theta is equal to 90 degree means that the plane will be 180 degree into theta in Mohr circle. Now take this plane, turn it to 180 degree, where it will reach here. Now at this plane, the intersection to the Mohr circle is sigma 1. Now at this plane, the stress will be sigma 1. Now what about the shear stress? There is no any coordinate for shear stress because shear stress is 0 in this point. But at every other point, like suppose this I taken as some angle. So it has two components, this component and this component. This component along with the origin is tensile, and around with the y-axis it is shear. So let me give you other question. Suppose you have a body and you have sigma 1 here, sigma 2 here. So by the equilibrium, we have also sigma 1 here, sigma 2 here. Now apply the same thing. So let us suppose sigma 1 is greater than sigma 2. So you have sigma 2 here, sigma 1 here. Now draw a Mohr circle in between. Okay, this is a Mohr circle. Now what will be the center? The center will be, what is this? This is sigma 2. What is this? This is sigma 1. So diameter will be sigma 1 minus sigma 2. Okay, this is the diameter. Now radius will be sigma 1 minus sigma 2 by 2, and this is the radius. and this is sigma 2. So what is the center? Coordinate of center? Coordinate of center will be sigma 2 plus sigma 1 minus sigma 2 by 2. So it will be sigma 1 plus sigma 2 by 2. Okay, so coordinate of center is sigma 1 plus sigma 2 by 2. Now take arbitrary any plane. Suppose I taken that plane and it is theta. So rotate this angle with 2 theta. Suppose this is rotated uh, from this plane in clockwise direction. So not clockwise, anti-clockwise direction. So rotate in that anti-clockwise direction. And you have 2 theta here. And now this is the value of shear stress because it is parallel to y-axis. So suppose this cut on Mohr circle at this point. So it has sigma tau as an axis. So then find the value. What is the sigma? Sigma is this. You have this value sigma. You have this value as tau. This is tau and this is sigma, the whole x-axis. So suppose this is O, this is A, this is B, this is C. Then OA is sigma, AB is tau. Any question? Anything that you're not understanding up to this point? Hello. Hello.
Sir, about the direction of rotation, sir.
Okay. Direction of
Theta.
rotation. Okay.
With respect to horizontal or with respect to vertical, which you should consider for theta, and in which direction you should take, sir?
Okay. I understand. So suppose you have a body. This is sigma 1. This is sigma 2. Now this is a Mohr cycle. Sigma 2, sigma 1, and you draw this. Now you need suppose that this is the angle I want. Now as you know, this is a sigma 2 plane. Now this has an angle of theta in anti-clockwise direction. If you look the direction of the plane from the sigma 2, what it is? Theta, okay, in anti-clockwise. And here the sigma 2 plane is this. Okay, then take anti-clockwise direction, means where the anti-clockwise will go. Anti-clockwise will go here. This is anti-clockwise. So take 2 theta from this plane in the anti-clockwise direction. Okay. Hello.
Yes, sir. Clear, sir.
Okay. Now suppose.
Okay.
Now suppose. Now how I am. You should ask now how I am right. Why? If I am taking this, so how I am right? So take theta is equal to 90 degree. If theta is equal to 90 degree, then what will be the plane of section? This is sorry. Let's write this line. So this is the plane of section. Okay, and here it is sigma. Now it is here it is sigma 2. Now if you take this body and at equilibrium here this sigma doesn't contribute in that plane, so it is only sigma 1. Hence the answer should be sigma 1 if you go by Mohr circle. Now put theta is equal to 90 degree, then what will be 2 theta? It will be equal to 180 degree. Rotate this plane from here to here in 180 degree. It will reach n to sigma 1. That is the point that I am asking. Okay. So any doubt in this point?
No, sir.
Okay. Now this is one thing. Now let's give a combination with shear stress. Okay. This is for the normal stress. And the same thing applies if compressive force comes. Suppose you have sigma 1 here and sigma 2 here. So you draw it, sigma 1 will be here, sigma 2 will be here, and now you draw the Mohr circle. Okay, and the same thing then can. Then you take the angle with the axis. Now the center of the axis is this, but the center of this circle will be different from it. It may be same, it may be not. So you need to take care of it, and you need to find the expertise in finding the coordinates. Otherwise, you will get very difficult to solve Mohr circle, because then suppose you have a point and you draw it like this. You have a point, you draw it like this. It is 2 theta. Then what is the Mohr circle? What is this value? Now this value is from center. From origin, you can obtain. You need to find the origin, but the value is coming like this. So what is the value of sigma? What is the value of everything? Need to be very good. Uh, just wait a minute. I'm coming. Hello. Okay. Now, if I am audible, say put something in chat box. Yeah. Okay. So now suppose this is a question. Okay, and you apply one force sigma 1 here, and sorry, you apply one force sigma 1 here. Because of equilibrium, sigma 1 will be in opposite direction. Now you apply a shear force here, suppose in this direction, tau. Now what will be the uh, what will be the shear stress and normal stress at this plane? So listen me properly. Because of this shear stress, you have a complementary shear stress in this plane. Okay, this is complementary. Okay, otherwise body will not deform. Now since the body should be in equilibrium, this is generating a moment in this direction. You need to counter attack this moment. So in this plane, this is the shear shear stress. Now let's draw the diagram again. This is your sigma 1, this is your sigma 1. If we apply a single shear stress tau 1 at any place, then it will automatically regenerate tau 1 at other surfaces also. That is called the complementary shear stress tau 1. Now, with this body diagram, now you need to find at an angle theta what will be the shear stress and normal stress. So let's take this plane. Let's take this plane. It has a value of sigma 1 and tau 1, but it does not have a value of sigma. It has only value of tau. Means suppose, so we assume sigma to be 0. Now, first of all, coordinate is sigma is 0, and here sigma is sigma 1. Now the sign convention for tau. For tau, we need to take clockwise movement as positive and anti-clockwise movement as negative. Oh, okay. I need to write it in couple of minutes. So in this, you need to take clockwise movement, clockwise direction tau as positive and anti-clockwise tau as negative. So what is the meaning of this? The meaning of this is, let me explain. Here you can see that here you can see that this is creating anti-clockwise movement, but this surface is creating clockwise movement. Means this surface has clockwise movement, but this surface has anti-clockwise movement. Now take this point and draw in positive. This is tau axis. Draw in positive direction tau axis as tau 1, and in this point draw it as a negative tau 1. Okay, now uh, take now take this line and draw it like this, and then from the center and touching this point draw a circle. That is very difficult in drawing in digital pen. Okay, so now everything got confused, I know. Let me clear one by one. So first, you know that sigma, from the sigma concept, sigma 1 is here and sigma 0 is here. Now from this axis, because this plane has, let me take another pen. Okay, now so from this plane you can see that this plane has zero normal stress, on only zero stress. So, and it is in clockwise direction, so take it in the positive clockwise direction, and here in this point is negative clockwise direction and same value. Now draw a line from here to here, then take this line as a diameter and with the center on the axis and draw a Mohr circle. Okay, draw a Mohr circle like this, and from this Mohr circle you obtain that the axes are now sigma 1 dash, sigma 2 dash. Okay, and you have something called the maximum value of tau 1 dash. Now that's what I am saying, you need to be very good in calculation. So sigma 1 is here, it is from sigma 1, this from this, so it is both sigma. Wait a sec, someone just came, I'm coming to my minute. Okay, so where I was, we need to find this value. So first of all, this is sigma is equal to 0, This is sigma is equal to sigma 1. Then what is the radius? It is sigma 1 by 2. So this value is also sigma 1 by 2. And this value is tau. So what if we apply the hypotenuse theorem, what will be the radius? Radius will be sigma 1 square by 2 plus tau 1 square. Okay, this is the radius. And if you multiply it by 2, 2 into sigma 1 square by 2 plus tau 1 square, this will be the diameter. Now, you know this point, this is sigma 1 by 2. You know this value because it is the diameter of circle, so it is the radius. This is r. So now, sigma 2 dash, what will be the sigma 2 dash? It will be sigma 1 by 2 plus the radius of the circle. And now, what will be the sigma 1 dash? What will be the sigma 1 dash here? It is the radius of the circle. This is the radius of the circle, and this is sigma 1 by 2. So it is sigma 1 by 2 minus r. Okay. Now, this, sorry, there is a slide. It is under root because otherwise that will be the square, hypotenuse square. Now, what will the maximum shear stress? Maximum shear stress is the radius of the circle. That is equal to tau max, and it should be equal to radius of the circle. And what is the radius of the circle? That is equal to under root sigma 1 by 2 whole square plus tau square. Now I ask what should be the shear stress and normal stress at angle theta. Now from this plane it is angle theta in counterclockwise direction. So just let me change the pen. Okay, so from this plane take sorry, now this is our plane that we are expecting. This is our plane. Now take this plane and rotate anti-clockwise into theta direction. Now this is anti-clockwise direction and this is 2 theta. And here coming, this is tau and this is sigma. Now at this plane, the value is sigma comma tau. Now I will discuss this in question, how to solve the value, how to solve it. Okay. So any problem?
Sir,
Yeah.
the circle meets the y-axis now, sir, at the top half.
The circle meets the y-axis where?
The tau one near left side, sir, left side.
Sorry, I didn't get your question.
The circle is intersecting the y-axis at no, sir, this point.
Here.
Yes, sir, that point. How to determine that point, sir? I didn't get that, sir.
Okay. So you know that at this plane, you have sigma is equal to 0. So your coordinate is sigma is equal to 0. Now at this plane, you have a shear stress tau 1. So move that point upward in the y-axis as tau 1 and point this as. So basically you point as like this, sigma comma tau. Now sigma is 0, so it is 0 comma tau. This point is sigma 1 comma minus tau because it has a anti-clockwise direction, so it will be minus tau. Okay, and point that value in that direction. I hope now you are getting it. That is a coordinate.
Yes, sir, it is clear now, sir.
Okay. So let me, I hope you have 15 minutes more before the lunch. So I am going with a quick questions. Okay. So let me take this one problem. Two problem. The first problem is first. Let's take this value. This is 100 megapascal, and this is compressive force 50 megapascal. Okay, and you have to obtain um, at an angle of so let me do this 25 degree. At an angle of 25 degree, what is the shear stress and the normal stress? So let's solve this question. Everyone please take out their copies, because if you do it with me, it will be helpful. So this is minus 50. Let's talk in terms of coordinate, because there is no shear stress. It is minus 50 0. It is 100 0. Right? Now draw the circle. Draw a circle. Okay. Suppose this is your circle. Now this is the circle. This is called the Mohr circle. You draw from this point. Now what is the center? Um, Coordinate of center. Can anyone say? Hello.
75,0.
25,0, right? Okay. Now it is 25 degree from this plane. Means compressive stress, from compressive stress it is, that is 50 megapascal, it is 25 degree. From this compressive stress plane, it is in clockwise direction, right? Am I right? So it need to be 50 degree, because it is 2 theta na? You know that. So it is 50 degree. Okay. Now what is the coordinate of this point? This is that sigma comma tau. This is what we want to obtain at 25 degree, and this is the value. Now suppose, what is the radius? Radius is 75 unit. Okay, because this is the radius, this is also the radius, and this is also the radius. Now what is the value of this? It is 75 cos 50. It is 75 sin 50. Okay. Now this 75 cos 50 is value is from this center, but we need to find value from this center. So this value is 75, and this is 75 cos 50. So your normal stress will be 75 minus 75 cos 50, and your shear stress will be same as 75 sin 50. So can you quickly give me the answer? Hello. 26.79. Okay. It is around that. Okay, 26.7. The answer is 26.79. This is, and what is the shear stress? Here 75 sin 50. Okay, 57.4. It is 57 point around 5 megapascal. Now you got this how to made. Now suppose this is only of tensile stress. Let's make it a little more complicated, and this is uh, this is 100 megapascal, and the shear stress is 25 megapascal. Let's take sorry, let's take the direction opposite. 25 megapascal. Now first of all, let's apply the equilibrium condition. It is 100 megapascal, therefore it is also be 100 megapascal, and this is the shear stress in this direction, so complementary shear stress put exert in this direction, then this direction and this direction. So how to remember it? Remember that on perpendicular planes, both the tips should be meeting. This is a term that you should use. Okay. So here also 25 megapascal shear stress and sigma is 0. Now uh, let's okay. Now it is over. Now let's draw the on Mohr circle. So first of all, the first coordinate is 25. On this plane, the coordinate is 0, comma 25, and on this plane, the coordinate is 100, comma 25. Now, what is the direction of 25? Here, it is clockwise direction, so it should be positive, and here it is in anti-clockwise direction. It is rotating in this way, so it is negative. Okay. Now plot this coordinate on Mohr circle. So 0, comma minus 25 will be here. 0, comma minus 25, and you have 100, comma 25 would be here. 100, comma 25. Draw a line in between and then draw a Mohr circle. So always okay. So this is your Mohr circle. Drawing this. Now this is your center. Okay, this is the center. Now I need to obtain at 20 degree, means suppose this plane at 20 degree. What is the normal stress and shear stress? So first of all, this is 100, comma 0. So what is the radius? This is 100, comma 0. This is 100, comma 25. So this is 50 and this is 25. So the radius will be under root of 50 square plus 25 square. Okay. Now take this is now we need to find values at 20 degree with the this axis at this is anti-clockwise direction. So this is your axis that I am talking about. Let's take 40 degree and plot it like this. Okay, this is 40 degree. Now this is your this coordinate is sigma, comma tau. Now you need to find this. How you will find it? Let me give you a hint. Okay. So first need to find out this angle, whether it is less than 40 degree or greater than 40 degree. Because if it is greater than 40 degree, then this line will end up here some. But if it is less than 40 degree, then this line will go up. Okay, I think you are getting it. So you need to find this angle first, and this angle is tan inverse. This is your 50. This is your radius. So radius half. What it will be? This is your radius. This is your 100. Okay. This is total 2 times under root of 50 square plus 25 square. This is this much, and you know this is the radius. So this is your radius. Now you know this, and yeah, I'm getting slightly elevated figure. Wait a sec. So this is your value. So this R is under root 50 square plus 25 square. Okay. Now you know this R, you know this 40. Oh, sorry, this angle you need to know. Okay. So we should get it because it's 25, 0. this is 25, 0. So this value is 25. Now you need to find out this angle. So perform sine inverse 25 upon radius. You will get this angle. Okay, you will get this angle by performing this sine inverse 25 upon radius. And the angle that came, you need to say that this is less than 40 degree. Now minus that angle, you will get this angle. And while getting this angle, you know the radius, just perform the same operation cos and sine, you get the shear stress and normal stress. Okay, but I need to solve this. I will solve it because time is getting over. You have only 5 minutes. So let me take some problems so that I can. Now, suppose you have, let's take a concept. I will after lunch, I will take that question. Okay, because that will take time. Okay, 26.56. Okay, someone had, okay, let's go. So it is less than 50 degree. So the angle coming is 26.56 degree. Now subtract that angle from 40 degree, and this will be your this angle. Okay, make this will be your angle, that is 40 minus 26.56. Now you know the radius. Then what will this stress be? This stress be r sine 40 minus 26.5, and your this value will be r cos 26.56. So this value is from this point, but you need to find it from this point. Okay, so the answer is, because you know this is 100, this is 100, and this is bisecting it, so it this is your radius. Okay, this is your 100, this is your radius, and it should be in between, that is 50. So 50 minus this point will be your answer. Okay, I will solve that after this after lunch. Don't worry, because the time is getting over. Now suppose the same question, you have sigma 1 here, sigma 2 here, you have tensile stress like this, tau. Here, if you draw the diagram like this, now you need to find the same as 20 degree. What will we do? So the operation will be like mount sigma 1, sorry, sigma 2, sigma 1, take the axis. So at sigma 1, it is anti-clockwise direction, so it is negative, and at sigma 2, it is clockwise direction. Take the value up, here down. So draw like this, create a circle. And now at 20 degree from this line, 20 degree means what is the direction? Anti-clockwise. So from this, sorry, clockwise. So clockwise from this, you need to go with 20 degree here, and that is 40 degree. So take this 40 degree, and this is your axis. This is your sigma comma tau. Okay. So I will meet after lunch, and I will ask you. I will give you the question and solve it. Okay. So when you will all will come? Can someone reply? Sorry, you are not audible. Very low voice. Hello. Okay, someone message. 2:30. Okay. At 2:30, I will go with the Mohr circle and then thermal stresses. Okay. Okay. You all can leave, and I will. Okay.